Chapter 10 Experiment. Aim
to determine the wavelength of a laser beam by diffraction.
Apparatus.
Laser source, grating, stand, screen, meter scale.
Theory.
Diffraction of light. The phenomenon of bending of light around the corners of an obstacle or hole is called diffraction of light. Diffraction effects are important when the size of the obstacle or the opening is comparable or less than the wavelength of light. The phenomenon of diffraction is a general characteristic of a wave, and it is exhibited by all waves like sound waves, water waves, matter waves etc. and is not limited to light waves only. Diffraction of light is of two types. 1. Fresnel diffraction. It is the type of diffraction that takes place at a slit when the source of light lies at a finite distance from it. As the source of light is close to the slit, therefore, the wavefront is either spherical in the case of a point source or cylindrical in the case of a line source in nature. The screen is also at a finite distance from the slit. 2. Frownhuffer diffraction. It is the type of diffraction that takes place at a slit when a plane wavefront is incident on it and the wavefront emerging from the slit is also plane. For this, both the source as well as the screen should be at infinite distance from the narrow slit. Diffraction grating. A diffraction grating is an optically plane glass plate, on which a large number of equidistant parallel lines are ruled. The ruled lines are opaque to light, and the spacing between any two ruled lines acts as a slit. Therefore, the ruled lines divide the glass plate into opacities and transparencies. The transparent slits, that is transparencies, transmit light. The number of lines in a plane transmission grating is about 6 × 10⁵ per meter. Let width of transparency, such as AB, figure 10.1 is equal to A. Width of opacity, such as BC equals B. Here A plus B is called grating element. When a parallel beam of monochromatic light of wavelength lambda is incident normally on the diffraction grating, all the points in each slit transparency become source of secondary wavelets. Suppose the secondary wavelets diffracted at an angle θ1 are brought to focus at the point P1 by the convex lens L such that secondary wavelets originating from A and C have a phase difference equals lambda, the wavelength of incident light. Therefore, the secondary wavelets originating from the corresponding points of any two consecutive slits will have a phase difference equals lambda. Consequently, all these wavelets reinforce each other and produce maximum at P1. It is called first principle maximum. It is clear from figure 10.1a that the path difference between the secondary wavelets originating from the points A and C and reaching at the point P1 equals Cn. From right triangle ACN, we have Cn by AC equals sin θ1 or Cn equals AC sin θ1 equals A plus B sin θ1. Therefore, for first principle maximum at P1 or P1 dash A plus B sin θ1 equals lambda 1. Similarly, for second principle maximum at P2 or P2 dash A plus B sin θ2 equals 2 lambda 2, and so on for the nth principle maximum A plus B sin θn equals n lambda 3. In actual practice, only a first few maxima are observed because the intensity of the principal maxima goes on decreasing with the increase of diffraction order. If the number of lines per meter on the diffraction grating is n, this value is written on the diffraction grating, then grating element A plus B equals 1 by n. Therefore, from equation 1, we get 1 by n sin θ1 equals lambda or lambda equals sin θ1 by n. 4. Similarly, from equation 2, we get lambda equals sin θ2 by 2n. 5. And so on. Knowing n, θ1, θ2, we can calculate lambda, the wavelength of light. Note: the diffraction pattern of a diffraction gradation is shown in figure 10.1b. Laser. A laser is a device that emits a beam of coherent light through an optical amplification process. A laser beam has the following properties. 1. It is monochromatic. 2. It is coherent. 3. It is high directional. 4. It has high intensity.
Procedure.
Take an optical grating of known value of n and fix it on the grating mount that is placed on a wooden stand. Allow the laser beam from the given laser source, helium neon laser or diode laser, to fall normally on the fixed grating. Place a screen on the other side of the grating to obtain the diffraction spots. Measure the distance d between the grating and the screen. Measure the distance between the central spot O and the first order diffraction spot on either side of the central spot, that is, the distances OP1 and OP1 dash. Find the mean distance, d1 equals op1 plus op1 dash divided by 2. Calculate the value of sin theta 1 equals d1 by square root capital D square plus d1 square. Calculate the wavelength lambda of laser beam by using the relation lambda is equal to sin theta 1 by n. Repeat the whole procedure 3 more times for different values of d. Find the mean value of lambda.
Observations and calculations.
Record all the observations in the following table and calculate the values.
Result.
Precautions. The diffraction grating should be vertical. Do not look directly towards the laser beam because it can cause permanent eye damage. Dark room should be used for doing laser experiments.